All right. On Friday, we were working on page 101, and we spent quite a bit of time drawing little tangent lines, estimating rise over run, and we eventually filled out this table. Okay, we practiced writing the equation of a tangent line. Okay, we're going to do that quite often this year. But what I want to get to in this section, go ahead. What I want to get to in this section is trying to take a look at this table and find a few patterns that can help us relate what a derivative, okay, slope of a tangent line, what a derivative is telling us about an f of x original graph. Okay, so take a second. These were our rough estimations of the derivative from Friday, and then this is what we said the graph of f of x was doing. Can we find any relationship or pattern between those two columns? We did tangent lines on Friday. That was just good practice. But for right now, I just want to focus on these two. What do you see?
If it's positive, it's increasing.
What do you mean by it?
If the derivative at that point is increasing, then, or if it's positive, the derivative at that point is positive, then it's increasing.
What do you mean by it is increasing?
I don't know what I mean.
Okay, this is, I'm glad you said that, and I don't mean to put you on the spot, okay? I don't mean to put you on the spot. Whenever you say the word it, okay, I do not want to see that this year. You need to specify what are you talking about, because on the AP exam, if you are not clear, you do not get the credit. So when you say since it is positive, then it is increasing, okay, by using it, you are not specific enough to communicate what you are trying to say. So try to refrain from using the word it. So can we try to say, again, what you're trying to communicate without it?
When the derivative
Yep.
at any x value
Yep.
is positive, then the function at that x value is increasing.
Perfect. No it. When the derivative at a specific location is positive, then the function, or f of x, is increasing. Okay, I don't want to see or read the word it. Okay, try to be specific. Are there any other ones? Notice how 4 was increasing, 2 increasing, 3 increasing. Love those. Anything else? See one cool?
When the derivative at a certain point is negative, the function is decreasing.
Perfect. Negative decreasing, negative decreasing, negative decreasing. Anything else? Keep going.
When the derivative at any x value is 0, the f of x is at a maximum or minimum.
Or a minimum. Okay, 0 max, 0 min, 0 max. Perfect. Can we get a little bit more specific and try to determine when specifically we have a max versus when we have a min? Because 0 can lead to either conclusion. Can we think about what makes it a max or a min? What do you think, Austin?
The function would be a max if the x value is negative, but the function would be a minimum if the x value is positive.
Okay, so when you say x value, you're looking over here?
Yeah.
So here's a max and it's negative, but notice how here's a max and it's positive.
Oh,
That's okay. At first glance, I can see it. What do you see, Griffin?
If the function is increasing on the left side
Uh-huh.
and then decreasing on the right side, then it's max. And
Okay.
then if it's decreasing on the right side, or the function's decreasing on the right side and increasing on the left side. Wait.
Left and right.
Yeah, you know.
I know what you
Then it's a
mean.
min.
Then it's a min. Okay, does that make sense? If you go from increasing to decreasing, that creates a high point. And if you go from decreasing to increasing, okay, that's a low point. So we're kind of going to look for that change in direction. All of those relationships we just picked apart on that table, we're going to write down on the next page. Okay, so flip it to page 102. At the top, we're going to write these down. So we talked about four different things. So without using the word it, we're going to say if. Now, instead of writing the derivative at an x location, because that's a lot of words, okay, this is when math notation is kind of important. Okay, so if we can say f prime of a, okay, the derivative at a specific spot, whatever a might be, whatever number you want, if the derivative at a specific spot is positive, but again, we can use a mathematic notation, if you're positive, you're greater than 0. So if the derivative at a specific spot is positive, then the function, or using math notation, you can use f of x, is increasing. What does the derivative mean again? Slope of tangent line. If your slope is positive, aren't you increasing? Makes sense, right? If the derivative is positive, if the slope is positive. The second thing, if the derivative at a specific spot was negative, less than 0, then the function is decreasing. All right, now the third one was if the derivative or slope was equal to 0. We kind of had that max or min pop up. So we're going to look at those two options. So if the derivative at a specific spot equals 0, and, okay, so if it equaled 0 and then had some type of change like Griffin noticed, we created a max or a min. So if the derivative equals 0 and changes positive to negative, so your derivative or your slope changes from positive to negative, meaning increasing or decreasing, then the function has a maximum at x equals a. Okay, that special x value. The other one was if the derivative equaled 0 and changes negative to positive, meaning decreasing to increasing, then f of x has a minimum at x equals a. I'm hoping those four things make sense based off of our current understanding of slope. If slope is positive, f of x goes up. If it's negative, f of x goes down. If the slope changes positive to negative, you create that max, and then negative to positive, you create the min. Okay, nothing new, but we're just relating it to a derivative. And so instead of saying slope, we're now saying derivative, but they're interchangeable. Okay, now on Friday, when we did all these estimations, okay, we had a graph to go off of, and we kind of drew little tangent lines to help us with that. But we might not always have a graph available to us. This is when perhaps a table might be more useful information or the only information we have. So we're going to try to see how we can estimate a derivative now based off of a table instead of drawing those tangent lines. And I kind of go into how we might do that based off the little paragraph at the top. So numerically, meaning using numbers from a table, the value of a derivative can be estimated by finding the slope of a secant line, okay, 2 points, passing through the graph on either side of the derivative location. So what I mean by that, and I'm going to try to zoom in on this little picture here. Remember when we drew this diagram in the previous section, we figured out where the limit came from? So I don't know if you can see the colors, but notice how this black line right here is the tangent line, and I labeled the point x sub t for tangent. If we're trying to figure out the slope of that black line, we can do this various different ways. We can pick a point maybe after the black line and then create a secant line, which would be the blue one. But notice how that blue line's slope is not exactly the same as the black line's slope. They're slightly different. Instead of picking a point after the tangent line, maybe you want to pick a point before the tangent line and then create your secant slope using the tangent point as well. That would create the red one. But notice how the red line's slope is not exactly the same as the black one's slope. So the blue is okay, the red one's okay, but we can probably get a little bit better. Notice how if you pick a point before the tangent spot and after the tangent spot, you can create that green line. And notice how the slope of the green line and the slope of the black line are relatively the same. Why? How are the black line and the green line related to each other? They're basically parallel, which means the same slope, right? So if you're trying to estimate the derivative based off of a table, instead of using the x location of the tangent line we want, we're actually going to use two different x values, one before it and one after it. Can we see why that's a better choice? Because we're creating a parallel line to the tangent one, instead of like the blue one or the red one that's not exactly parallel. Okay, so it can get confusing, and you're going to see why in a moment. If we take a look at the table, okay, the first derivative we want to estimate is the slope at 0, if you can see that. Okay, so we want to figure out what is roughly the slope at this location if we were to plot these and kind of get a graph, assuming they were connected in a nice way. This is when it gets confusing. Notice how the x value of 0 is given to us on the graph, or sorry, on the table, but the best way to estimate the slope at this point is to actually pick a point before it and after it, because you'd be creating a parallel line, or to the best of your ability, a parallel line. So we're actually not going to use the point at 0. Do we see why that can be a little confusing? Even though it's asking you for it, we're not going to use that point. You could, okay, it would be an estimation, but not the best one we would have. Because if you actually use the point at 0, you would be creating the blue line or the red line. But notice how the green one would be better. So to estimate the derivative at 0, we're going to find the slope between those 2 points. Okay, that secant line slope. So we can use y2 minus y1 over x2 minus x1. Okay, a point before it and a point after it. So it looks like we'll get negative 5 over 4. That's a rough estimation for the slope at this spot. Now, based off of that slope value, what can we say f of x is doing? Increasing, decreasing, max or min? Decreasing. Why? Slope's negative. The derivative's negative. Perfect. All right, just for practice, we're going to do another tangent line example. What do we need to know to write the equation of a line? Point, slope. All right, so point, this is coming from the function itself, so we need to figure out f of 0. And then the slope comes from your derivative. We got to figure out f prime of 0. Now, we already have that estimation. That'd be negative 5 over 4. The point value, f of 0, can actually come from your table. If you plug in 0, you get out 1. So point slope, we can put them together. Y minus the point equals your slope times x minus the tangent location. Do you guys think you can do the other 3? Give it a shot. Okay, very similar to the ones we did on Friday. You're estimating a derivative, you're determining increasing, decreasing, max or min, you're doing tangent line, but instead of doing a graph, you're now using a table. Okay, different piece of information. Try the next 3. How did we do? Pretty good? Gotta go over any of those three? All right, this train's moving. So, we first started off looking at a graph, okay, estimating a tangent line, then we just moved on to a table. What we're going to get into probably throughout the rest of this unit is analyzing a graph, whether it's an original graph or a derivative graph, and seeing what information we can conclude about the other function. For instance, if they give us a g of x graph, what do we know about g prime? Okay, the derivative. If they give us a g prime graph, what do we know about g of x? Okay, the original function. We're going to start to draw these connections between the two, and it basically always comes back to these four connections that we just developed from the chart. Okay, so this is basically what we're going to be looking for a lot in this unit. So on page 103, they tell us at the top that this is the graph of g of x, so this is an original function, okay, no derivative or anything like that, and we're going to try to determine based off this graph where some of these derivative values are true. So if this is an original graph, we got to think about the connection between what an original graph looks like, or what an original graph is doing, and how that's related to, for instance, this first one, where is the derivative less than 0? Okay, meaning negative. So what's that connection we should be identifying between this graph and that notation to help us determine these x values, or these intervals? G prime means derivative. If your derivative is less than 0, your derivative is, yeah? All right, if your derivative is negative, less than 0, then the original function is decreasing. Okay, that's our connection, one of the patterns we saw from the chart. So where on this graph can we give the intervals where this graph is decreasing? If you were to trace it left to right. There we go. -4, -2. So this little section going down, yep. Is there another one? Go ahead, Christian.
Is it 1 to infinity?
Yep, so we'll throw in the u and do 1 to infinity. Good. For those of you that had me last year, we did a lot of this. Increasing, decreasing, above x-axis, below x-axis, intersection points. It was towards the beginning of the year, but we did a lot of it. All right, next one, g prime, meaning the derivative, is greater than 0, aka positive. So if your slope is positive, we got to think about what is the original function doing. What do we think? Increasing. So let's go ahead and give those intervals. Yep. Yep. So this little piece definitely going up. -2 to 1. Perfect. All right, it also says give reasons for your answer. So for the first one, we'll say because g of x is decreasing, and for the last one we just did, because g of x is increasing. Okay, they wanted a reason, so we'll give it to them. All right, values for x where the derivative is 0. Your slope is 0. -4, -2, 1, because g of x, the original function, has a max, relative max if you want to use that word, max or min. Perfect. So notice how at those spots you'd have those horizontal kind of flat tangent lines. Okay, so this is bringing up something that we got to get used to in terms of our justifications. Notice how the information they gave us was a g of x graph. So every single justification should state something about the g of x graph. If this is what they give you, you have to use it as your reasoning. Okay? So we got to take a look at what we have and use that to help us justify what we know or what we can conclude. Okay, we'll get to an example on the back where this is a derivative graph, but before we get there, I do want to introduce a new line. So far we've talked about tangent line and secant line. Okay, there is something called a normal line, and maybe you've heard of this in a physics class if you've dealt with normal vectors, perhaps. But a normal line is simply the line perpendicular to the tangent line. So what do we know about the normal line? If it's perpendicular, yeah.
Its slope is the opposite reciprocal of the tangent line.
There we go. So slope is opposite and reciprocal. Okay, we'll get that to a second. Okay, but it still comes back to like those algebra concepts with slope, parallel lines, perpendicular lines. Okay, it's revisiting us in calculus though. So pictured to the right is the function of the quadratic. Okay, just as a refresher, notice how we can kind of conclude that this makes sense because notice how it moved left 1, up 4, and the vertex is flipped, okay, or the graph is flipped upside down, so kind of makes sense. So it says draw the tangent line to the graph at x equals 1, and then estimate the value of f prime at 1, so the slope at that point. So just like we did on Friday, if you went to the x value of 1, plotted that point, and then to the best of your ability, drew a tangent line, what would the slope of that tangent line roughly be? Okay, they're asking us to estimate it. So we'll use those little squiggles. Can we calculate rise over run? What does it kind of look like it should be? -2? Okay. Mine looks like down 3 over 2, with the way I drew it, so that'd be -1.5. Okay, but still pretty close. All right, something around there. So this was your tangent line. Notice how it only touches once. They now want us to find an equation of this tangent line that you drew. Okay, so we need what? A point, and I'm gonna beat it into you guys this year. Probably beat isn't the politically correct term, okay? But I'm gonna drill it into you guys this year. So we know our slope is roughly -2, or whatever you estimate it to be. The point value comes from the function, and that point we plotted was +2. So point slope, y minus the point equals the slope times x minus, bless you, tangent spot. So our question now is, if this is the equation of the tangent line, okay, that's what we drew here, let's go ahead and try to figure out the equation of the normal line. So the line that would be perpendicular to this one. How do you think we can use the information we already know to help us write the equation of the normal line? What do you think, Anush?
Wouldn't it be the same equation, but you just change the slope to 1?
There we go. Okay, so it's the same equation because it goes through the same point. Okay, so we still have that information, but instead of being the derivative value, the slope of the tangent line, we need the opposite reciprocal value of that derivative. So that would be 1/2. Okay, so it's just changing your slope value. It still goes through the same point. Now, if we actually drew it, okay, going through this point, and notice how it has a slope of 1/2, we can draw that in. All right, there's our normal line. Notice how it would create kind of a 90-degree box. Okay, so a new line to our vocabulary. Instead of tangent line and secant line that we should be familiar with, we now have normal line, but that just means perpendicular. Okay, let's go ahead and try a derivative example. So this time, okay, the graph at the top is representing h prime of x. Okay, so this is not an original function graph. This is the slope of h of x. Okay, it's a little different. So we got to ask ourselves, what are these connections? If this is the derivative graph, and we want to figure out where h of x is increasing, what should we be analyzing about this graph? What do you think, Griffin?
Where the graph greater than 0?
When the graph is greater than 0, where this graph is positive. Okay, because we said the slope has to be positive. So my $1 million question to you is, where is this graph positive? Yeah.
Where it's above the x-axis.
Where it's above the x-axis. Okay, so if I wrote the notation f prime of x is greater than 0, okay, this is technically a y value, like f of x is. Okay, if the y value is greater than 0, we want to be above the x-axis. So it looks like, if we actually highlighted those in, we need to write those intervals. So we go from -2 to 1. Should we use brackets or parentheses? Why?
It can't be 0.
It can't be 0, right? So if you're on the x-axis, that means you're equal 0. Okay, we want to be greater than 0. So we'll throw in a u and then do 3 to infinity. Okay, now it says give a reason for your answers. So because, now since this was the graph of a derivative, that's what we have to use as our justification. Because the derivative, we said, is positive, okay, greater than 0. Graphically, it's above the x-axis, okay? Any of those phrasings or wordings would be fine. What about the next one? H of x is decreasing?
Below the x-axis.
Below the x-axis. Okay, so before we even identify it, we'll say because h prime of x is negative, you can say h prime of x is below the x-axis. Okay, any of those is fine. So we have the justification, we just got to figure out where that is on the graph. So where are we below the x-axis? Yep. So that little piece. And 1 to 3. That little piece. Perfect. All right. Then it gets good. Where would the original graph have a maximum? Maybe we want to approach this one like we did the last one. Can we think of the justification before we actually try to figure it out? Because maybe that will help us figure it out in the end. What do you think, Anush?
The derivative has to be increasing then decreasing?
Not the derivative.
Oh,
The original function. Okay? So the derivative has to be what? What do you think, Austin?
The slope has to be 0.
Slope has to be 0 and something else. Because if it was 0, we said it was a max or a min. There was something else that clarified it if it was a max versus if it was a min. Yeah.
The slope of that, or no, not the slope, like the y value is changed from positive to negative.
Okay, so the derivative equals 0 and changes positive to negative. So if your derivative changes positive to negative, that means, like Anush said, the original function is changing, increasing to decreasing. Okay, so let's see if we can figure that out on this graph. Where is this graph equal to 0, but also changes from a positive value to a negative value? Yes? 1, good. So you equal 0 because you're on the x-axis, but notice how before that point you're positive because you're above, and after that point you're negative because you're below. So we'll say x equals 1. That's a specific spot. All right, the next one we're trying to figure out a minimum. So before we even get there, maybe we can think about what we need to find. So if we're at a minimum, what are we looking for? The derivative is what? 0 and changes negative to positive. Okay, so we got to find that on our graph. So where in this graph is the derivative, or is the graph 0 rather, not the derivative 0, is this graph 0 and changes negative to positive? -2 and 3. Okay, so we equal 0, we're negative before, positive after, and for 3 we're negative before, positive after. So we have x equals -2 and x equals 3. 2 spots. Are we hanging in there? We're doing okay? All right, let's try some other ones. If h prime of -1 is a half, what is the equation of the tangent line? All right, we need to know what equation of a tangent line? point slope. Okay, point slope. Now they give us the point. Notice how it's just h, not h prime. So h of negative 1 is a half. Where can we figure out the slope value? We need h prime of negative 1. What do you think, Griffin?
The y value on the h prime graph.
All right, this was the graph of h prime, the graph of the derivative. So if you were to plug in negative 1, notice how your value would be 5. So the slope value is 5. It's not the slope of this graph, like we looked at previously. This is the graph of slope. So any output you get is representing the slope. So we just got to put those two together. Y minus the point equals the slope times x minus the tangent location. Let's check out the next one. If h of 2 equals negative 3, what's the equation of the normal line? So it's still a line nonetheless. We need a point and a slope. They give us the point. We got to figure out the slope. What do we think? What do you think, Anuj?
The slope of the tangent line
Mhm.
at 2 is negative 2
How'd you get that?
from the graph of h prime.
Okay. All right, so the tangent line slope is negative 2. So then what do you want to do from there?
That means the perpendicular, the normal line
Yep.
is 1/2.
There we go. So if this is the tangent slope, we need the opposite reciprocal of that one. So that would take you to the normal slope. So we got to put those together. Y minus the point equals the slope times x minus the tangent, or normal point in this case. We doing okay? All right. So I would say these 4 connections that we did on 102, we're going to be seeing a lot of those the rest of this unit and in future ones. Okay, so if you seriously think about these, how they're related to slope, I'm hoping they make sense. Like if your slope is positive, you're increasing. Slope is negative, decreasing. Slope is 0. You have a max or min. We got to keep those straight. Okay, but we're going to be spending so much time on this. I'm hoping it's going to kind of become second nature. Okay, we'll stop there for today, and we're going to pick up the next section tomorrow. And I think it's going to be kind of an aha moment for us tomorrow. We're going to get to derivative shortcuts. So instead of using that h limit, okay, a lot, we're going to see a quicker way to do it. And you guys might be mad at me for not showing it to you first, but we'll talk about that tomorrow.